Thank you, KDD, for having me here. For some of you who've seen me I've been coming to KDD for a couple of decades, and in many avatars of mine, student, applied researcher, and now as a startup founder. And the company we formed, and this is Yuri Liskovic, myself, Vanya, and the entire team behind PyTorch Geometric. We came together to form a company called Kumo. And this is the story of what motivated us to build the platform, the technology behind it, and why we think graph learning is so powerful, right? And I'll also talk a little bit about the open source that we put out there, and the team is also here, so you should feel free to even, for the students, if you want to collaborate on the open source, that's a great avenue as well. So all of us who formed Kumo came out of the same pain that we wanted to solve in our previous jobs. And I'll tell you a little bit about my own journey here. And I started my career in NLP and IR. I used to publish in SIG-IR, and my first paper was on language models for query ambiguity. And these were not large language models. I had 512 MB of RAM, and I have some lab mates in the audience who will remember those times. And we were trying to, build statistical methods that would actually beat rule-based systems. So back in 2000, the way we did question answering was, or the winning systems in question answering were extremely rule-based, right? So the winning systems used to analyze text for parts of speech, word-sense disambiguation, named entities, and so on and so forth. And there were these large feature engineering pipelines that used to take years to build and were hard to beat at that point with the kind of computing that we had. And over the years, over the 2 decades or more since then, the computing revolution, you don't do feature engineering anymore. You give raw text to a transformer architecture, and it learns everything, right? So, and this was about the time in my career when the transformer papers came out. I'd actually moved to the adjacent space of recommender systems. And I saw this revolution that was happening in the field of text, which was my original field, but recommender systems. And I was working on recommender systems at LinkedIn. My co-founders were at Airbnb, Pinterest, and companies like that. And our systems in recommender systems looked as hairy as the QA systems of 2000. And so the systems looked like this. They were, we were chaining pipeline after pipeline after pipeline, and then we were serving them in production. You don't have to read the entire slide, but it's just saying how many little, tools that a data scientist. So we were hiring these really smart people, but they just had to learn so many tools in order to be successful in their jobs. And it was a pain. Every time you had one system that had a bug, debugging was a pain. So this made us, wonder as to, what are the workloads in our system, in our companies. And it was actually nice to see how Shun also had the same taxonomy. And really, in our companies, we had 2 kinds of workloads, generative and predictive. And the generative workloads were the ones on which text, the video, image data was being operated on. And the revolution was really happening for tasks there on summarization and conversational bots, data extraction, all of those kinds of tasks. But the predictive workloads, the personalization, the ads recommendation, the CTR prediction, next best action, these were all the predictive workloads, and they were the ones that were looking, circa 2003. And they were all operating on private data. So then we started asking ourselves the question as to what is the kind of data that these predictive workloads are on. And we found the uniform answer across company after company that we spoke to, that the data was laid out in a relational form. And that made sense because, we were starting to index petabytes of data in all our companies, and we were laying them out for analytics pipelines. And analytics also saw, leaps in the kinds of tools that they had, like really beautiful visualization tools built on, relational schemas. And the AI engineer who had to operate on these relational schemas still, though, had to do a lot of joins and a lot of crazy SQL gymnastics to get their data in ready for ML. So that was the pain that motivated, the kind of platform that we wanted to build. So I'll double-click and go into an example of a very simple, three-table example. You have a customer table, a transactions table, and a products table, right? And let's say there's one user, and she has a transaction in April, and then one in June. And you're building a churn prediction model. It's a simple model. It's a binary classification model, and you want to say, is the user going to be active or not in a given month? It has great use cases because based on the prediction that the user is going to churn in the next month, your marketing team might want to send a notification, or you might want to do some kind of action that brings her back into the platform. So extremely useful for the business, but hairy to build. And why? Right, so the labels here are, in May she's active, and in in May she's churned, and in June she's active, right? So in order to generate these labels, what our data scientists have to do is what we call time travel on the databases. So what they end up doing is first, they'll say, okay, I'm going to use a certain time window to do my feature generation, and I'm going to do another time window for my label generation, right? And then you don't want to use features from the label generation period in your feature generation period, because otherwise you have information leakage and your models won't do great on an A/B test, right? So what you end up is you start writing SQL for each timestamp. So you start creating labels for, as I said, May, April, June, and so on and so forth. And then you write features corresponding to every timestamp. So your May features need to look at data only up to May. Your April features need to look only up to April, and so on and so forth. And that was one of the cruxes of the large number of pipelines that our teams were building. So we said that's one level of automation. This is going to be something that we're going to make really, really easy for the data scientist. And then, of course, there is serving these models in production. So then how do you mirror the features in offline where the data scientist is in the lab, and how do you bring that to production? So that has led to a farm of model stores, feature stores, and so on and so forth. And for us, we felt like, hey, we can make all of this really, really simple. And really, we said, how do we take away feature engineering, right? So coming back to that analogy of QA systems, how do we take that feature engineering away? How do we take this time travel business away for the kind of problems that we're looking at? How can we design ML systems to leverage data in the natural form, and the natural form here being in its relational form? And relational form can be just Parquet files on your S3 or whatever data storage you have, but it can also be, your database inside your company. And then we said, can we make predictive AI or predictive ML as easy as the analysts have for SQL, like life has easy for the analyst? And can we make it as easy as asking ChatGPT a question? And then we said, how could we make our data scientists, or how can we make the data scientists in our organization empowered to find more use cases to drive value for the business, as opposed to doing all of this, crazy gymnastics with workflows, and it takes months to write a model, and so on. So we said, there must be a good algorithmic way to solve this, and that's what brought us together. So for the idea behind Kumo, the platform, and when I say Kumo, it's the name of the company, but it's also the name of the tool. But the idea behind Kumo, the platform, is actually, you just have to get two concepts together. One is that all predictive AI tasks can be expressed in a domain-specific language. And we actually have a very SQL-like DSL for this, and I'll tell you why it is so easy to make into an algorithm. And the second is that all predictive AI tasks can be mapped to a graph problem. So when these two ideas come together, you can suddenly create a platform that is much more efficient and performant than what we do today. And I'll show you evidence in use cases that we work on, both in the open source as well as with our customers. So for the first part, our DSL looks something like this. And it's SQL-like, but with a predict clause. So you have a predict operator, and on the predict operator, you can have any kind of aggregation function. Aggregation functions let you specify regression-like tasks, but you can also have greater than, less than, equal tos, and so on and so forth. And our documentation contains the entire gamut of operators that it allows, but it either maps to classification or regression. And really on a data warehouse task, if you have a very a normalized schema, you're typically doing predictions over an entity. So for each, like in SQL, works really well. And then if you're a data scientist, sometimes you like to constrain your training window sizes. And a where clause with SQL-like syntax lets you play around with that. And then it was beautiful and elegant, because once we wrote it out and we could go use case after use case and actually say we can always express it in this language, that was one big aha moment for us. So here are a couple more examples. One is a forecasting example. One is a link prediction example, or a recommender system example, where the list distinct operator is telling you what are the transactions that are going to happen over the next 7 days for this customer. So that's your typical link prediction kind of problem. And we have a rank operator as well. So with a limited set of operators, we were able to express any ML problem. So that was our first innovation. The second observation that we had was this training table that I talked about. I had that timeline, and I had the label generation period. In that, the training table that you create, or the table with the labels, is really down to 3 columns, and it's always the same regardless of machine learning problem. So whether you're classification, regression, multi-label, link prediction, or forecasting, it's these 3 columns that matter, and you just have to have flexibility on the kind of schema that you have for your label. So once you have these 2 pieces together, observation 1, which is you have a DSL, and the second one that you have a training table, which is a standard schema, it says, let's take our predictive query language, let's write an algorithm behind it, and let's create a training table. And that's a beautiful level of automation for a data scientist. And that's pretty much what the predictive query side of it does. It's agnostic to the GNN, but it's a very powerful framework for Kumo. Now, this took away the pain or the SQL gymnastics, as I said, that we do for the label generation part. Now, what about the feature engineering part? I haven't talked about it yet. And that's where the GNN comes in, right? So in terms of the GNN, I think what you have to capture from this part of the talk is that all predictive AI tasks in a relational database can be mapped to a graph neural network. Now, let's come back to that 3-table example. And you have a customer table, you have a product table, and you have a transactions table. Customers can be nodes on this graph. Products are again nodes on the graph, and the transaction table, through its key linkage, can be mapped to edges on this graph. And this pattern is again extremely repeatable in a standard relational schema. In addition to this, in addition to mapping a relational schema to a graph schema, we also find that we need to index time as a first-class citizen into the graph representation. And why that is important will become clear in the next slide. But what we do before I talk about how we get away from feature engineering is we combine that idea of the training table to the relational graph. So these two constructs come together, and now we have a very powerful representation on which we can do machine learning, and we can do any machine learning problem that you can define with our predictive query language. So for this, if you're familiar, if you work in the field of graphs, maybe this is easy for you to see. But otherwise, it might take some time to dwell on it. But pretty much all predictive ML problems can be either mapped into a node problem or a link problem. And within node, you have classification, and then you have regression. So if you think of churn, it was a node classification problem because we're saying, is this user going to churn for a churn? Next best action could also be framed as a node classification problem. You could also think of regression problems like lifetime value, like what's this user's spend going to be on the platform over time, right? You can have link classification problems, and you can have link regression problems. So a lot of these problems that we were seeing in the predictive ML space that I defined earlier can be reduced to one of these four, right? So it's these set of observations that made it easy to build a platform that generalizes to any ML task. Now, why? And we talked about time, right? Time was the pain which was making a lot of these tasks so coding intensive or resource intensive in some ways. So by indexing time and applying GNNs, we get away with a lot of the feature engineering problem. To understand why indexing time is important is, I won't go into a tutorial on graph neural networks here, but something you need to understand on GNNs is during training and inference, you're always creating subgraphs. And you're creating, and the subgraphs are time dependent. So if I'm training for the main node, I may use one subgraph, but if I'm training for a later in-period node, I would use a different subgraph. When you index time, you can actually make the subgraph sampling algorithm time aware. And that's the trick we use. So we don't have to do training and test splits. We just index the graph. And then when we're doing subgraph sampling, we're able to take care of time in there. And that's the cute trick that we've applied. So we have one representation on which we can do so much. That said, now GNNs, again, this conference has been a delight for us from Kumo because there's been so many GNN papers and we're just so happy to see them used in so many use cases. But just to get the idea of why they're so useful, effectively you have node representations and nodes learn from their neighbors' representations, right? So you get a bit of the birds of a feather flock together kind of phenomenon going on during the message passing. So if I buy a lot of red shoes, my node embeddings should keep updating in a way that makes me similar to other people who buy a lot of red shoes. You can also encode different node types, edge types into these rich algorithms. Over time, we've also had to innovate as we worked with different customers. And we put out a new algorithm in the upcoming Baylearn conference. It's called Hybrid GNN. And this improves over PinSage and or GraphSage and other algorithms that are out there. And effectively what it does is it lets us combine. GNNs do really well when you have repeat purchases, right? But in many applications, you don't want to be over-rotating on repeat purchases. You do want to be able to be looking at new items and so on and so forth. And I think in the earlier talk in this track, there was the talk about the milk chocolate and the dark chocolate examples. So and if you don't want to be, it is possible that a dark chocolate user likes milk chocolate as well, right? So how do we solve for those kinds of problems? And the hybrid GNN does really well on that. And then in terms of the Kumo architecture itself, right? So we can, over time, so again, a lot of the product features or user features may have textual columns in them. So we've actually made vectors a first-class citizen. So you can call your favorite LLM, whatever open source LLM that you want to use, you can call it, you can bring those encodings as node features directly. And to us, it's just a column in a database. Whether it's an image, it's a piece of text, it's call an encoder and bring in those embeddings and use Kumo for the sparse cross-attention that you need to capture the relational features. So then you put all of this together and you have a platform that is more efficient and performant. And what do I mean by efficient and performant? On the slide up here is a very compact notebook. So you're not writing so much SQL. You just have, I don't know how visible it is, but you pretty much connect your data sources, you define your graph, and then you write a predictive query, and then you call train, and then you call predict, and then you're mostly done. You let things run under the hood. So it's a huge efficiency play. But then there are data scientists who love tuning the graph neural network because they're not happy with the first model and you want to squeeze more juice out of the model. And we do emit the parameters. But that's where we want the data scientists to spend time on, as opposed to the data engineering that comes to bringing data into building ML. So we expose all of the parameters for the graph as well as the standard ML norms. So we did a hackathon earlier this spring. We sourced people from our LinkedIn networks, and we took a data set that we had never worked on. So it was a MyAnime data set. It's a set of animation movies and a recommender system problem. And our data scientists just did one model out of the box, and then we gave our documentation. We did some office hours, and we taught people the platform. And that was our test of how easy is this predictive query language going to be that people can onboard and actually start building models on. And actually, we had 17 signups, and 12 people survived till the end. So that's not too terrible for a hackathon, because people get busy and drop off, and maybe some people dropped off because the platform was hard, but it was pretty delightful to see these people, because within the first day itself, they were running over 33 training jobs. And by the 5th day, they had run 353 predictive queries. So these 15 people had run that many queries, and they had run 2,000 plus experiments, because each predictive query forks off into a number of experiments because you're playing around with parameters under the hood. So that was that's an example of the level of productivity that a data scientist can get with the Kumo platform. But it's not just productivity, because on this chart is the accuracy improvements. So the yellow line there is just how popular animes does, so that's the baseline. The red line is what our data scientist did just to test the platform, because it was a new data set and we just didn't want to break in front of the public. But over the 5 days, the blue curve is what the participants did, and they were able to improve performance by over 200% in those 5 days. And you see this over and over again. So again, in the ADS papers track, I think the LinkedIn GNN paper was out there. And again, they talk about use case after use case where they are finding GNNs successful and useful. But again, GNNs are not easy to build, and therefore that's where that was one of the motivations to build Kumo, which was to bring in other companies and partners who want to be able to use this technology to enable and empower their data scientists. So we have many partners, and some of them were brave enough and great collaborators who were early adopters. So one example is DoorDash, who uses Kumo for to power their try something new notifications. And in fact, a lot of the hybrid GNN innovations came from that design partnership, because a lot of the observations of the kinds of, people didn't want the same restaurant over and over again, right? So we needed to show some new restaurants as well. And the metric lifts, I can't report them here, but they were static even in MAU. And those of you who know, who work in engagement in consumer companies know that unique user metrics are very hard to move. So they had significant lifts in MAUs and revenue as well. This is iFood. This is another partner. They're out here in the audience with us, and again, food delivery. So again, significant lifts both on recommending restaurants as well as sponsored results. And then this is a slightly different use case. This is Whatnot, and where we worked with them for item-to-item recommendations. So if you're looking at shoes, can we show you other shoes? But the interesting thing about Whatnot is they're a dynamic marketplace. They're like an auction marketplace. So inventory items are unique. So things come in and go out very quickly. And in this case is where we needed to see that actually using the content of the item, so the text, the image, is going to be really important. And this was where we, using the LLM features to, enrich the representations of the items turned out to be super useful. We've branched out since from food and delivery, and actually now we work with partners in health as well. And this is a use case of forecasting emergency room volume. This was our first forecasting use case, and it was not easy to get a GNN to work on forecasting. And this data set had all kinds of idiosyncrasies and all kinds of spikes. But with the ingenuity of our team and bringing in additional features. So while we look at your data warehouse, you can also bring in features like, in this case, we brought in the US holidays as a table, and that's the calendar is another table, right? It's an external source. You bring it in, and it tells you that, oh, there's some seasonality, and the model starts capturing seasonality. This is a UK bank that we work for. And this is a money muling use case. So again, it's about finding customers who are moving proceeds of crime. Hard use case, and we see this repeated pattern again in fintech, that GNNs do just really well at capturing patterns in transactional data. This is a B2B business. They wanted to predict whom their sales team should reach out to. So their sales team was reaching out ad hocly to people based on intuition. And they said, hey, we want to do this in a data-driven way. They were using a marketing tool. And, we said, let's do some lead scoring for you. And in a double-blind study, the Kumo model did, significantly better than what their marketing tool allowed. So again, across these use cases, we've been able to see both the predictive query and the GNN generalize well. This is an auto insurance customer. It's body injury prediction, right? And in this case, the auto insurance customer also kept a log of what their workflow was like. So we had a very nice side-by-side comparison of them doing feature engineering, which was completely reduced to zero with the Kumo platform, And then there was some time spent, so there were 7 days spent in model development on the Kumo platform. That's mostly iterating on predictive queries and tweaking model parameters. And they had similar, a development cycle. And then there was the model deployment side of things. So huge productivity and model performance benefits. We've been putting out some of this work in open source as well. And you can look us up. We have 2 libraries out there, PyTorch Frame and PyTorch Geometric. What Kumo does is help you scale over these open source libraries and gives you very simple abstractions that you don't need a team that's an expert in graph neural networks. But again, even in the open source, students and data scientists find similar productivity and model performance improvements. These results are published. But productionizing for so many customers brings its own set of challenges, and also a set of requirements that we learned as, we're all researchers turned technologists turned founders, and we had to think about certain considerations. The first one was explainability, because every one of our customers, and particularly in the case of health and insurance, but also in recommender systems, needed to be able to explain to their boss why was the system recommending A over B, right? And so we've had to innovate on explainability. We had to think about security and privacy. We had to think about making sure that our systems are compliant. We had to think about scale, cost, and building a system that's performant and meets SLAs of the customers. On explainability, if you had a chance to visit Matthias's talk, it goes nicely into the details of the explainability algorithm innovations that we've had to do. But at the core, we're able to go down up to column level importance, but we've been able to go down to prediction level, explaining why a particular recommendation was made for a particular user, showing the graph and the set of features that the GNN picked, right? So it's rare for a GNN algorithm to be able to, or a neural network algorithm to have explainability, but this was a place where a customer needs forced us to innovate on the science side. On scale, we're able to do 30 billion edges today easily and serve them with production SLAs. We've built a system, so we have a graph engine and a feature store, both of which let us distribute the graph. So our PyG implementation is a single machine implementation, but the Kumo implementation lets you distribute the features, the node features across multiple CPU machines and just index the graph in GPU. And this is extremely performant and cost effective. We also had to think about security. So we had customers in fintech who would never want their data to leave their ecosystem. So we started partnering with different data warehouses to say, how do I deploy Kumo down in the containers where your data warehouse lives? So again, from for ML practitioners, we've made it very easy that you don't have to think about these things, and we have a tool that lets you, deploy in any mechanism, and we'll take care of that for you. But both from a security and privacy considerations, we have multiple variants that, satisfy customers with different business needs. People use us in production by stitching us together in their workflows. So often, data lies in their data lake. Kumo comes in, predictions are put out. We're a batch prediction system, so we write data back to your data lake. And then you may use us in your email targeting, your search tools, your ad campaign management tools. We have just many different integrations that our customers do. And use us for serving. So that's us. We're a team that's spread across different locations, and we're hiring, but we're happy to collaborate with anyone in this community, both on research as well as on the product. So I'm happy to take questions at this point.